So in this video I'm going to explain to you how to build any kind of functions just from a bunch of sine functions, sine and cosine functions. That said, I'm not going to give you the full recipe. The full recipe is what you learn when you study Fourier analysis. Right? And that would go well beyond what I can teach you in a single lecture or even a couple of lectures. So I want to get the idea across of how it works. So let's imagine we've got some kind of wave shape that is a sort of sawtooth like this. So this is my wave. So it falls off really steeply and it does this. So I'm just drawing it on my screen right now. And it goes off. Okay. So this is clearly not a sine function. Not a cosine function. It's not, no matter what frequency you pick, you're not going to get these points. But we're going to try to approximate this function with sine and cosine function. And I prepared this over here. So let me start. Let me pick one sine function that I think might sort of maybe do the trick. There. So this is the function I want. That's what I got. Okay, not very good. It's not remotely close. Yes, it goes up when this one goes up, but then, I mean, terrible. Alright. I'm going to modify it. I'm going to add a second function, and don't worry about how I figured out that I have to multiply it by 2 over pi, and how did I get those values? Doesn't matter. The point is I'm multiplying a sine function with a second sine function of different frequencies. So let's add that. That's the green one. I'm getting rid of the blue one. So you can sort of see how it makes a valiant attempt at representing this function. Of course, you would never guess those values. You never say, I bet it's 2 over pi times sine of pi x plus 2 over 2 pi times sine of 2 pi x. You wouldn't guess those, but there are ways of finding them based on the function you're starting with, the function that you want to approximate. Those methods are beyond what I'm going to teach you right now. You should look them up yourself, go online, find out about Fourier analysis. Okay. Just showing you how it works. So this is two functions. I'm going to add a third term. This is this one here. 2 over 3 pi times sine 3 pi x. So you notice a kind of a pattern here, right? It's 2 over 1 pi times sine 1 pi x. 2 over 2 pi sine 2 pi x, the minus sign. Now it's a plus 2 over 3 pi sine 3 pi x. Yeah, I take this one away. It's this one. It's getting better, right? It's getting... It's still a little weirdly wobbly and misses the endpoint, but it's getting there. It's improvement. I can extend this pattern further, so now I'm going to add over here a term 2 over 4 pi sine 4 pi x. I'm going to get rid of this one to this one, and again, getting better. Now, of course, typing those in by hand is a bit of a pain. So I'm helping myself with a functional expression. If you're wondering the whole time, what's this thing up here? I'm going to come to that right now. So all I've written out up here is exactly this pattern, right? Sine of n pi x, n is 1, 2, 3, 4, and so on. And then it gets multiplied by 2 divided by n times pi, 1 times pi, 2 times pi, 3 times pi. And the minus sign here, minus, and then minus 1 to the n, that just fixes that it's plus then minus, right? So this sum is really just a shorthand of writing this. Let me switch to this one here. Okay. So right now it's terrible because I only have my sum going from the first n to the first n. So it's really, right now, this sum is really just the first expression I had here, right? I make this 2. Okay, that's what we had before. We make it 3. Oops, this is 4. This is where we ended, right? This is the same function as this one here. Right? But now I can add more terms. I could have done this manually, but I'd still be here 10 days from now. So I just wrote down the general form of this. Let's go to 5. Getting better. How about 6? Yeah, we're getting there. How about 10? Oops, did I mess up? I did mess up, didn't I? Oh no. Let me type this in again. Goodness. Alright, sum from n equals 1 to n equals 10. There we go. Not sure what happened. Okay. can tell our red function does a pretty good job at this point to approximate the blue one. Not perfect, but it's doing a pretty good job. How about we go to 100? Is it going to let me? Yeah, there you go. I mean, you can hardly see the difference now. Slight differences at the very top, the very bottom. The corners are sort of a bit funny, but beyond that, it's a pretty straight line. Let's zoom in a bit. Oops, it doesn't help. I mean, what I drew on the screen just stays, but you can see there's a little bit of a wobble here in the function, but it does a pretty good job of approximating the function that I want. It is now shifted out of place. There we go. Right. Probably just get rid of this. Okay. So you see how this gets us the sawtooth function extremely well. Let me see how far it lets me go. If I put in 1,000, is it going to explode? Nope. Works perfectly well. You can hardly tell the difference now. A little bit here again at the endpoints. Looks perfectly like the sawtooth function we wanted. But it is a sum of 1,000 different sine functions. Sine of 1 pi x, sine of 2 pi x, sine of 3 pi x, 4 pi x, and so on. Each one multiplied by a different value, right? And the value here is fairly simple. It has this pattern of 2 over 2 pi, 2 over 3 pi, 2 over 4 pi, 2 over 5 pi, and so on, with plus and minus signs alternating. A different function, it's not the sawtooth function, is going to have some other values here, right? It's not 2 over 2 pi, it's going to be something else. If I just play around with it, let's see what happens if I just take away the minus 1. What happens then? Actually, it's not actually too different. Interesting. So let me put a minus 1 back in. You get the point, right? I can build this function here just by adding lots of sine functions, and the more sine functions I add, the better my approximation. It's not perfect. Let's zoom in, zoom in, zoom in, zoom in. There's a teensy bit of a wobble. There you go. You zoomed in really far, and you can tell it's not actually a straight line. But it's doing such a good job to approximate it. And I could imagine going to 1,000,000, right? Be totally indistinguishable. So this was for a, machine, can you rebuild it? Thank you. So this was for a function, right, that repeats, like a sawtooth function, that's called. Can figure out what it is for like a sort of solid square function as well. It's just different values. For a pulse, now I want a pulse. A pulse is something that doesn't repeat, right? You sort of wobble your string up and down once, what are you going to get? So for that, get rid of this. Let me go to this one here that I prepared. So in this case, I've got a function here. I'll show to you what that looks like. That is pretty flat. And then there's a little single bump in the middle. Right. Now, how did I build this function? Like, it doesn't repeat. There's just one little bump in the middle. I still build it from sine and cosine functions. In this case, a sine function. Now, this looks complicated because it's an integral. Remember, an integral is just a sum. So the difference, what I had to do here compared to what I was able to do here, is that here I just take sine of pi x, sine of 2 pi x, sine of 3 pi x, essentially discrete frequencies, or the angular frequency pi, angular frequency 2 pi, angular frequency 3 pi, and so on. For this one here, I added an infinite number of sine functions together. Remember, an integral, right, is a sum. So I get a sum of these sine functions, where I summed all the values of w, right, and it's my integration variable, from 0 to 1, and, you know, there's some constant in front of it. But the x is here. This is just a sine function of x with some angular frequency omega, w in this case, plus a constant that happens to be w. Actually, could change this up a bit, and then it'll look like this. It'll change the shape a little bit. So maybe I could even just not have it be w. Oh, did I break it? Oh no, I broke it, didn't I? Let's go like this. Right, so I can get this kind of shape as an infinite sum integral is an infinite sum going all the values of w. So I start at w equals 0, w equals 0.0001, w equals 0.0002, w equals 0.0003. And I add all those sine functions, each one multiplied by some factor that in this case depends on that 0.0002. Now again, how did I get this exact expression? 2 over w. And how did I know to put w here, not pi w here? And what about this one here? Again, how to derive the expression that I want for a specific shape of pulse, that's a different story. Right? Take a class that has Fourier analysis in its description somewhere. It'll explain it to you. The point is, I can do it, right? I can build a pulse like that as a sum of sine functions. And a sine function satisfies the wave equation. It's allowed. The sum of sine functions, say 2 sine functions added up, still going to satisfy the wave equation. You can check that. Right? If 1 sine function makes it true, then 2 of them make it true too, provided they have, say, the same wave speed. 3 sine functions added up, they still satisfy the wave equation. Again, plug it in, work it through, convince yourself that I'm telling the truth here, but you got to do it yourself. An infinite sum is still going to satisfy the wave equation. We could literally take this expression with the integrals and plug it into the wave equation and see what happens. Of course, we'd have to make it move first, but we know how to do that. You have to replace x by x minus vt. And that's how you get any function to move. Doesn't matter if it's a function that involves an integral. Replace x by x minus vt, and you get that whole shape move to the right with speed v. And as long as v is what the wave equation says it has to be, you're gonna be fine. Right? This function is allowed according to the wave equation because it is a sum of sine functions. That's enough on that stuff. So I really recommend you take at some point or another a course that involves Fourier analysis, especially if you're a physics major or math major. You probably have to anyway if you keep going on that course, but the sooner the better, because it is extremely useful in all sorts of areas of physics that involves waves. We're going to come back to it at least twice, once in the context of music and analyzing sound waves, and once in the context of light and analyzing color. Alright, thanks for watching.